Hold up a coin. Any coin. It feels solid. It feels like nothing could possibly be inside it. You already know that's wrong. You learned it somewhere along the way. Maybe in a classroom, maybe from a documentary. Everything is made of atoms, and atoms are mostly empty space with a tiny dense center. It's one of those facts that sits in your head so comfortably, you've probably never questioned how anyone figured it out. But here's the strange part. For most of human history, nobody had any way to know that. The inside of an atom was not just unknown, it was assumed to be unknowable. And the person who finally cracked it open didn't set out to find what he found. He was trying to prove something else entirely, and the universe handed him a result so bizarre, he almost didn't believe his own experiment. To understand how strange this discovery really was, you have to go back to 1897, to a physicist in Cambridge named J.J. Thomson. Thomson was studying cathode rays, the glowing beams that shoot through a vacuum tube when you run electricity through it. Nobody knew what these rays actually were. Thomson figured out they were streams of tiny, negatively charged particles, far smaller than any atom. He called them corpuscles. Today you know them as electrons. This was a shock. Atoms were supposed to be indivisible. The word atom literally comes from the Greek for uncuttable. Thomson had just found something smaller than the smallest thing. So what did the rest of the atom look like? Thomson proposed an idea that became known as the plum pudding model. Picture a sphere of positive charge, like dough, with negative electrons scattered through it like fruit in a pudding. It was neat, it was reasonable, and it was completely wrong. But nobody knew that yet, because nobody had a way to look inside an atom and check. That changed at the University of Manchester in 1909, thanks to a physicist named Ernest Rutherford and two collaborators you've probably never heard of, Hans Geiger and Ernest Marsden. Rutherford had already won a Nobel Prize for his work on radioactivity, and he had a favorite tool for probing matter: alpha particles. These are small, fast-moving, positively charged particles thrown off by radioactive elements. Rutherford's plan was simple. Fire a stream of alpha particles at an extremely thin sheet of gold foil, thinner than a human hair, and watch what happened on the other side. If Thomson's plum pudding model was correct, the prediction was easy. The positive charge in the atom was supposed to be spread out, soft, diffuse, like fog. A dense, fast alpha particle should punch straight through with barely a wobble. Rutherford expected to see a faint, even scattering, almost all of it in a straight line. He handed the actual measuring work to Geiger, a meticulous experimentalist, and to Marsden, who at the time was still an undergraduate student. Most of the alpha particles behaved exactly as predicted. They sailed through the gold foil like it wasn't there. But Rutherford, being thorough, asked Marsden to check whether any particles were bouncing back at extreme angles, just to be safe. Nobody expected to find anything. It was almost a formality. Then Marsden found some. Not many. Roughly 1 in every 8,000 alpha particles didn't just deflect slightly. It bounced almost straight back, as if it had hit a wall. Rutherford later described his own reaction in a line that has survived because it captures the moment so perfectly. He said it was as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. That is not a subtle result. That is a result that breaks your model. Why? Because you can't bounce something backward off a soft, diffuse cloud of charge. You can only do that if you hit something small, dense, and heavy, concentrated in a tiny space. Rutherford spent almost 2 years thinking through the implications before publishing, in 1911, a new picture of the atom entirely. Almost all of an atom's mass and all of its positive charge, he argued, is packed into an incredibly tiny core at the center. He called it the nucleus. The electrons orbit around it at a relative distance so vast that an atom is, by volume, almost entirely empty space. If you scaled an atom up so its nucleus were the size of a marble, the whole atom would be roughly the size of a football stadium, with the electrons somewhere out near the seats. Did Rutherford know he'd just redrawn the map of matter itself? Not immediately, not fully. His model still had a serious problem. According to the physics of the time, orbiting electrons should lose energy and spiral into the nucleus in a fraction of a second, meaning atoms shouldn't exist for more than an instant. That gap was closed a couple of years later by a young Danish physicist named Niels Bohr, who applied a brand new and deeply strange idea called quantum theory to explain why electrons can only occupy specific, stable orbits, like rungs on a ladder rather than points on a ramp. Bohr's model, combined with Rutherford's nucleus, became the atomic picture that eventually made its way into every science classroom. Here's the part that's easy to miss. Rutherford wasn't trying to discover the nucleus. He was mapping out how alpha particles scattered, mostly to understand radioactivity better. The backward bounce was a footnote he almost didn't bother checking. An undergraduate student ran the measurement that ended up unraveling 12 years of accepted physics. That's not how discovery is supposed to work, according to the tidy story most people imagine, where a genius sits and reasons their way to the truth. Real discovery is often what happens when you check the boring control experiment nobody thought would matter, and it refuses to behave. It's also worth sitting with how invisible this all is to you, right now, in your ordinary life. You cannot see an atom. You certainly can't see inside one. Every material you've ever touched, every breath you've ever taken, is built from structures 100,000 times smaller than a human hair can even hint at, arranged in a way no one confirmed with certainty until just over a century ago. The device you might be reading this on works because engineers understood electron behavior in exactly the way Thomson, Rutherford, and Bohr pieced together. Medical imaging, nuclear power, the periodic table itself making logical sense instead of being a list of memorized facts, all of it traces back to a gold foil, a beam of alpha particles, and one unexpected bounce. What's remarkable is how fragile this chain of discovery actually was. If Rutherford had skipped that backscattering check, assuming it was pointless, the plum pudding model might have stood unchallenged for years longer. If Geiger and Marsden hadn't been painstaking enough to notice a signal that showed up in less than one particle out of every 8,000, the anomaly could have been dismissed as instrument error and buried. Entire scientific pictures have collapsed on evidence far more obvious than this, and still taken decades to be accepted. This one held up because 3 people took a strange result seriously instead of explaining it away. So the next time you pick up that coin, or any solid object at all, remember what you're actually holding. It looks solid because your senses were never built to perceive the truth at that scale. It looks continuous because the empty space inside every atom is far too small and far too fast-moving for your eyes to register as anything but solid matter. What feels like the simplest, most obvious fact about the physical world, that things are made of stuff and that stuff has a structure, was unknown to every human being who ever lived until just over 100 years ago. It took a Nobel-winning physicist, a meticulous lab partner, an undergraduate running a routine check, and one result so unexpected it nearly broke the equipment of belief itself. Hold up that coin again. It still feels solid. But now you know what's actually inside it. Almost nothing at all. And, right at the center, almost everything that matters.